Let's go back way back. 13 billion years ago, the very first stars in ancient globular clusters were born. Now, by all the rules we know, they should have cooled down and faded out eons ago. But right there among them, some objects are, well, they're refusing to act their age. You see, astronomers started finding these stars that just looked wrong. They appear twice as young, and they're way hotter than their ancient neighbors, even though we know for a fact they all formed at the same time. These are the celestial troublemakers we call blue stragglers. So what we have here is a paradox, right? A seemingly young, hot, massive star hanging out in a cosmic retirement home where only ancient, dim stars should exist. Now, to really grasp just how bizarre this is, we first need to understand the fundamental rules these stars are so clearly breaking. So, first things first, let's establish those rules. We've got to look at the basics of how stars are supposed to live and die. This is pretty much the number one rule of stellar evolution. A star's entire fate is basically sealed the second it's born. The bigger it is, the more massive it is, the hotter and faster it's going to burn through all its fuel. Just think about a star that's, say, 10 times the mass of our sun. Its life is incredibly bright, but it's also incredibly short. It'll burn through its entire fuel supply in only 20 million years, which is just a blink of an eye in cosmic terms, before it goes out in a blaze of glory as a supernova. So, as a star gets older and the hydrogen in its core starts to run out, its whole internal balance just gets thrown off. It starts to swell up, puffing out dramatically and transforming into what we call a red giant. And when that happens, its gravitational grip on its outer layers gets really, really weak. Its atmosphere basically becomes vulnerable. And the scale of this transformation is just immense. A star's radius can balloon by 200 times. To put that into perspective for you, if our own sun became a red giant, its outer layers would completely swallow Mercury, then Venus, and they'd reach all the way out to the orbit of Mars. This makes that outer atmosphere a prime target for any star that happens to be nearby. And that brings us to our first major theory explaining these blue stragglers. You can think of it like a cosmic crime scene, where all the evidence points to a very long, very slow theft. The whole process kicks off in a tight binary system, where two stars are orbiting each other. As one star puffs up into that red giant phase, its partner's gravity sees an opportunity. It takes advantage of that weakened hold on the outer layers, and, well, this is how stellar cannibalism gets started. So here's how it goes down. The red giant's bloated atmosphere gets pulled away by its denser companion. Now, this stolen gas doesn't just fall straight onto the other star. Instead, it flows across the system, forming this superheated, swirling disk of material, an accretion disk, that spirals around the vampire star. As the receiving star gobbles up all this fresh hydrogen, its mass starts to increase. And all that added weight cranks up its core temperature and pressure, which effectively restarts nuclear fusion. It gets a brand new lease on life, allowing it to jump back onto the main sequence. That's the stable, adult phase of a star's life, and stay there for billions of years longer than it ever should have. But that's just one way to make a blue straggler. There's another, much more dramatic path. This one isn't born from a slow theft, but from a direct, head-on, violent collision. And we have really strong evidence for this. Data from the Hubble Space Telescope confirms that in the chaotic, jam-packed cores of these globular clusters, direct star collisions are 100 times more common than they are in the emptier parts of space. It's just cosmic bumper cars in there. When two stars collide in these super crowded neighborhoods, the outcome is a total merger. They basically combine everything, their mass, their fuel, their momentum, into one single gigantic new star, a rejuvenated behemoth. The potential scale of these mergers is just staggering. They can produce objects like R136A1, a star that clocked in at an estimated 265 times the mass of our own sun. That's way beyond what we think is possible for a single star forming the normal way. So, a star has managed to get a second life, either by sipping from its neighbor or through a massive collision. But this stolen youth, it comes with some really profound and measurable consequences. So what happens next? This is where the physics gets absolutely fascinating. Snagging all that new material and all that momentum leaves a permanent mark on how the star behaves. A huge side effect is extreme rotation. You know how an ice skater pulls in their arms to spin faster? It's basically that, but on a cosmic scale. By absorbing all that swirling matter, these stars hold on to the angular momentum and spin up to incredible speeds. We're talking about rotation at the equator that can hit 5 kilometers per second. That's 10 times faster than the spin of Earth's surface. Now, these oddball stars are more than just cosmic curiosities. They're actually historical records. By studying how many blue stragglers there are and what they're like, scientists can essentially create a dynamic clock to measure the history of all the interactions within that star cluster. For instance, if astronomers look at a cluster that should be ancient, but they find that a whopping 20% of its stars are blue stragglers, that's a huge clue. This high number tells them that the cluster must have had a history filled with intense, chaotic, and violent gravitational encounters. But here's the thing about borrowed time. It can't last forever. The very mass that gave the blue straggler its youth is the same thing that seals its ultimate violent fate. Because of all that mass it picked up, the star's end is going to be swift and spectacular. It's destined to end its life in a violent supernova explosion. Within just 3 million years, a fleeting moment after its long second life, it will collapse under its own weight and become either a hyperdense neutron star or even a black hole. So in the end, the blue straggler, the star living on stolen time, is both a record of cosmic violence and a unique laboratory for understanding how stars work. Its very existence proves that even in the oldest corners of our universe, something new can emerge from chaos, and that sometimes even the most established rules are meant to be broken.